Okay, so we have Julia here talking today about tensor product and support varieties for finite tensor categories.
Thank you so much. I want to thank Arik and Dan for this invitation. I'm very pleased to be in the seminar, and thank you for all of you to be here listening to my talk. Yes, I want to talk about tensor products and support varieties for finite tensor categories and Hopf algebras. A lot of the things that I will say are for Hopf algebras, and this is based in some joint works with my co-authors Peter Bergh and Sarah Witherspoon for this more like general context of finite tensor categories, and with Sarah for some examples in Hopf algebras. And I will mention maybe some results with Chris Negron. So let me tell you first very shortly some motivation for this work. So the idea is that we have this word of algebra. Maybe I will be talking usually about non-commutative algebras. And then we have here on the other side algebraic geometry. So some geometry. So the idea is that we want to understand some objects here, in particular, maybe representations of non-commutative algebras, or maybe in this other more general context, objects in finite tensor categories. And how we will do that? We will study something that was proven to be very, very useful in the theory of groups or representations of groups, that it's called support variety. And what we will do to connect these things is, or we will connect these things via cohomology. So we will use cohomological methods to take these algebraic objects and get some geometrical objects out of this and get some information of them to then be able to say some things about the algebraic objects again. So that's kind of the idea of what we will be doing. So the idea of the talk is that I will introduce the things here, the Hopf algebras and the tensor categories, and give some examples. And then I will tell you about cohomology in these finite tensor categories, and then how the support variety can be defined in this context, and some properties. So let me start with Hopf algebras. I will always assume that K, just in case, is an algebraically closed field here. The characteristic might change depending on the case, and I will tell you about that. But if I don't say anything, I'm just thinking that it's algebraically closed. So what is a Hopf algebra? A Hopf algebra is, first of all, a K algebra. So it will have a multiplication M and a unit here. So this is my multiplication, my unit. And for being a multiplication and a unit, I want to have them satisfy certain conditions. I want the multiplication to be associative. And I want the unit basically saying that this algebra is unital. So here I want to do identity tensor M. And I'm writing it in diagrams because it will be useful for the next step. But what I want, this is saying that the algebra is associative, and I will have a similar diagram for the unit. Or not similar, but maybe another diagram for the unit, for saying that this actually, it's giving me a unit for the product, for the multiplication. So I don't want only to have this algebra structure. I want to have also a coalgebra structure on my object, on H. And so what is that H is also equipped with a co-multiplication. And basically what I'm doing is you see that the multiplication goes from A tensor A to A. The co-multiplication will change the direction of the arrow. So I will have a map from A to A tensor A, and the same, the co-unit will be a map, and now I'm changing the direction of my arrow. So I will have a map from A to the field K. So this is the co-multiplication. And here my co-unit. And now I want to have also some properties, and I want that my my co-multiplication is co-associative. And what I will do is I will copy this map here, or this diagram here. As I told you, what I did before was to turn my arrows. So that's what I will do in my diagram. Basically, we will get the co-multiplication being co-associative by changing all these directions of the arrows. So it's like we are dualizing somehow our diagrams. I mean, possibly it's not the most natural way to read now the diagram, but the idea is that you get a similar diagram, but just by changing the direction of your arrows. So the idea is to have a dual structure that it's this co-associate or co-algebra structure, and I will have another diagram that will be dual to the diagram for U, but for epsilon. So I can obtain this diagram from this one by doing the same as I did for this diagram. So this is my associativity, and this here is my co-associativity. But I want to say that now I have two structures, and I would like some compatibility between them. So I will ask for some other thing. I will ask that the maps delta and epsilon. So I want compatibility between this algebra structure and the coalgebra. And how I will get this, I will ask that the the co-multiplication and the co-unit are algebra maps. So that they behave nicely with the multiplication. So delta of H F is the same as delta of H times delta of F. And the same for epsilon. And if I have these two things here, what I get is something called a bialgebra. To be a Hopf algebra, I need to have a condition being satisfied by my bialgebra. So having a bialgebra is kind of adding extra structure on this algebra structure that I start with, is adding this coalgebra structure, and there could be different choices. But the next step is just something that you can check if exists or not. And it's the existence of an antipode, which is a map from H to H that must be an anti-algebra map. And this needs to satisfy certain, so what I mean with this is if I have S of HF, I get S of F times S of H. So it's not multiplicative, it's multiplicative if you put here H op. And op means the opposite multiplication. And of course, I want not just this map, I want this map to behave nicely with all these things here. So I will get another diagram. Actually, we'll have two diagrams, but I will write only one because of, as you can see, I use a lot of space already. So let me move this a little bit here. But I will write only one of the maps. The other one, the other diagram is exactly the same. So what I will do is I will start with H. And one thing that I could do is I could apply sorry, I changed, for some reason here I wrote A and it was all the time H. I don't know why. I'm sorry. All these are H, not A. For some reason I got crazy and I changed my name for the Hopf algebra. So what I could do is I could pick H and go to the K with the epsilon, with the co-unit. But then if I'm in K, I can use the unit to go back to H. And now what I could do is if I have H, other thing that I could do is use my co-multiplication, go to H tensor H. And here is why I have two maps. I don't want to apply immediately M. I want to use this S, and I will use S tensor identity here, but I could also have another diagram using identity tensor S. So here I will still go to H tensor H, and now I will multiply. So the other diagram comes from interchanging these two things, and I want this to be commutative again. This diagram, or this antipode, what it's doing, it's kind of being, in some sense, playing some role of an inverse, in some sense, because you will start with something and you will get almost something that it's the unit here, but you have multiplied by this epsilon. And in the other side, what you are doing is you are multiplying one of the factors here, you are modifying it by S, and then you are doing the product of these factors to go back to to H, and that product is almost H is almost the original element, but it's modified by the counit. One last thing that I want to say is that I usually will use Swidler notation. And that means that when I write delta of H, even if this doesn't need to be only a factor and could be a sum of elements, I will write it as H1 tensor H2. Here in our mind, we have a sum. It's not exactly that, but this is a common notation for Hopf algebras, and this just means that it's the first component in this sum of the co-multiplication. So if I do something, I'm doing it to the first summands here, or the first factors in the sum. That's what I mean. And it's not just that it's a pure or an homogeneous thing. It could be a sum, and it could be some scalars and things, but we will use this Swidler notation. So these are the Hopf algebras. Why Hopf algebras? Why we study this structure? What they have that are special about them? And I will answer that after giving you some examples. One thing that is special is that they you can give Hopf algebra structure to some other algebras that we know very well, and that will be useful because what I will say in 1 minute. So if we start with a finite group, there are two nice Hopf algebras associated to them. One is KG. This is just the group algebra. So I will have just linear combinations, maybe not A here, maybe, or maybe C sub G, G here. Sorry, not for C sub G in the field. Here G in G. So this is just the group algebra. So what it will be the Hopf algebra structure? Here, what I will do is you give me one of these elements in the basis. I will just give you kind of something diagonal. I will just give you two copies of the same thing. The counit is just 1, and you can find that the only antipode that you can define because of the defining property is G inverse. That's why I told you that it's plays the role of the inverse. And in the group example, you can see it by doing the calculations of what needs to be satisfied, and what it happens is that must be the inverse of the group element. And then you can extend all this by linearity to get how it behaves in this group algebra. The other example that I want to say is the algebra of functions from G to the field. So we will have, you can think it in this way, but are basically functions from G to the field, and a basis of this vector space is given by Px. Here X will be an element in G. One comment is that the multiplication will be given in this way. So if I have Px times Py, what I will say is that this is 0 if y and x are not the same, and Px if they are the same. So what you are seeing here is that they are orthogonal idempotents here, yes, and they are central also. So what it's here, how we will do the co-multiplication, what we will do is, let's say that I start with Px. What I will do is I will have all the tensors that when you multiply the indices here of your basic elements, you get x. So I will do this. So are all the ways that I can get x from multiplying the label of this and this thing. Then epsilon of Px will be just will be 0 if x is not the neutral element of my group, and will be 1 if it is the element. So E will be the neutral element of G here, and here we have P of X inverse. That's how, and again, we can extend these functions by linearity. So these are two nice examples of Hopf algebras, but there are many others. And a lot of things, a lot of nice examples come from, or quantum groups are a nice collection of examples also. And let me tell you why I like Hopf algebra so much. If you look at, or why they are very interesting, and maybe I don't need to say this here, but why they are very interesting is because of the representation theory. If you look at here rep H, and what I will mean with rep H for me will be, I think I say it below, I will start with a Hopf algebra here, and I will work with a finite dimensional Hopf algebra. I already put it here, but it will be for me finite dimensional, and that means that it's finite dimensional as an algebra over K. And I will use the notation that we were saying. I have a multiplication, unit, co-multiplication, co-unit, and the antipode. So what I want to look at, it's the category of finite dimensional H modules. So I want all the representations of this Hopf algebra H that are of finite dimension. That's what I will look over my field K. So why I say that these Hopf algebras are very nice? Because in general, if you take two modules and you do the tensor product, in general, it doesn't need to be a module again. But in this case, because we have the Hopf algebra structure, we have that the tensor product is again an H module. And how we do that? And maybe one way of inspiring us is remembering that, for example, the group algebra is a Hopf algebra, and we know how to do that in groups, right? For rep of a group. What we did, or what we usually do, is we use the diagonal action. And here we will do the same. So actually this will be via the commultiplication. And remember that I will write this commultiplication using Sweetler notation. So how I act now in V tensor W, and then I will extend this by linearity. I just act in the first factor, so I act in V with the first factor in my commultiplication with the H1, and I act in W with the second factor of the commultiplication. So this is kind of a generalization of the diagonal action, or what we actually call in Hopf algebras also the diagonal action. It's just acting via the commultiplication. And something nice is that, again, we have that the field is a representation, and this is kind of the trivial module for the Hopf algebra, but in this case, we will need to act via epsilon. We will use epsilon. So if now I want to know how H acts in 1, it will not be just 1, it will be modified by a factor of epsilon of H, that, if you remember, this was something in the field. And what this is nice is because now this trivial representation, in some sense, it's called the trivial representation because it's kind of a unit for this tensor product. So if here now I place K, it will be isomorphic. So if I place K here, this will be isomorphic to W, not just as a vector space, but also as a module over H, because of the compatibility, or because this is a co-unit for the commultiplication. So that axioms play well together, because give me that this representation is the unit for the tensor product. And the other nice things is that the dual have also a structure of H module. And here we will use the last piece of information. We will use the antipode. And actually, I should say that I can use S and S inverse. Since my Hopf algebra is finite dimensional, the antipode is invertible. Sorry, invertible, because H is finite dimensional. And actually, I can induce two kind of actions. I will write one, but I will tell you both. So if I have now F in V dual, and I want to see how H acts in F here, I would like this to be something again in V dual. So what I will tell you is how, or what this function is, by telling you how it behaves when I plug in something in V. And I have here, I want to use F of B in some way, because this is something in the vector space. But I want to modify it via the action of H somehow, because V is a module. So what I will use is, I will use that I have S inverse of H acting on V. And actually, we can define two kinds of duals. One is called a right dual, and the other is called a left dual. One is defined using the inverse, and the other is defined just using S. So we will use these to define two kinds of dual. The other one, usually we put the dual on the other side as a vector space is the same, but it has a different module structure. So these are all very nice features that the category of representations of a Hopf algebra have, and that's one of the things why we like, or why I like Hopf algebras. And I don't know if you have questions up to this moment. This is a good moment to ask questions if you have some. Okay, if not, now I would like, this is a good example to keep in mind, because now I want to introduce to you finite tensor categories, and kind of Hopf algebras or representations of a finite group are my thing to keep in mind if I want to, if I want to think about what are the nice properties that I want in a finite tensor category. So let me tell you what is a finite tensor category. And here I should say over the field. Here the field is important. So over K. So what is a finite tensor category? It's a category that basically has all the nice properties that we just saw in representation of the Hopf algebra. So the first thing that I want to have is an abelian structure. So I want this to be an abelian category. That means to have a direct sum of a zero object for the direct sum. And I want my objects to, my morphisms to have kernels and co-kernels. And I also want, and here is where the field plays a role, I want this category to be K-linear, meaning that when I look at the morphisms between two objects in my category, this must be a K-vector space. That's where the field will play a role. Instead of being just a set of arrows between the objects, I will have a vector space. This will have certain extra structure. The other that I want, or the other structure that I want in my category is to be monoidal, which is what we were just seeing, that if I have objects in there, I will have this bifunctor that is the tensor product. So you can take two objects and get a new one using the tensor product. This tensor product needs to be associative. And in category theory, we will not use equalities anymore. So we will not expect X tensor Y tensor set to be equal to X tensor Y tensor set, but we expect them to be naturally isomorphic. And so that's what the associative constraint is doing, is telling me how to change parentheses when I have three objects. I want to have a unit object. This is just another object in the category, that it's the unit for this tensor product, meaning that if I have one tensor X, that must be isomorphic to X. And for that, I will use this natural isomorphism map again, because I cannot say that they are equal. And if I have X tensor 1, I also want that to be isomorphic to X via this left map that will give me that isomorphism. And of course, I want all this to be coherent. So I will have a pentagon axiom and a triangle axiom. And let me tell you very quickly in words what this means. This means, what is this pentagon axiom telling me? That the way to put parentheses is coherent. So if you give me 4 objects, I have 5 ways to put parentheses on them. That will be the vertices of my pentagon. And this will be basically a commutative diagram. And the arrows will be the morphisms between them. That will be associativities. And maybe associativity tensor the identity of some of the morphisms. So basically, it's telling you that all the ways to put the parentheses are coherent. Even if you pick one, you can go from one to the other using this thing. And this triangle axiom is relating this and the identity map, basically. The other thing that I want, as we saw before, so here we are already seeing that we have the tensor product and the unit, that this was kind of the commultiplication and the epsilon. Now we want the rigidity, and this rigidity means that I have duals, and here I should say left and right duals. Here I'm just writing one of them because they are similar and I don't want to use all the space in this, but the dual is not just another object, it is another object, but it's equipped with 2 maps. One map that could be kind of familiar, it's called evaluation. You see that you have something in this dual tensor, the element, and that should be a map that goes to the unit. If you are in vector spaces, it's actually the evaluation of vector spaces, what you will be looking here. And this is, it's kind of the opposite direction going, but if you see these two things are switched, this is called the co-evaluation. And when you are in vector spaces, and that's why I require my representations to be finite dimensional, for this to exist and satisfy one axiom that they need to satisfy, the vector space need to be finite dimensional, and what you will do is you will send your element 1 in your field to the sum of the dual basis. And I mean, for this sum to be finite, the vector space needs to be finite dimensional. This is a co-evaluation, and you can prove that if it's infinite dimensional, you don't have it. So this behaves very similar to the things that we have in vector spaces, but it's kind of the categorification of that. And so here you need to have some so-called zigzag axioms. That what tells you is that basically if you compose after doing some rearrangement of things, the evaluation and the co-evaluation map, and maybe you need to use these maps here too, then you will get the identity. So it's kind of a nice zigzag diagram, something like this if you're familiar with graphical, sorry, I did both the same way. If you're familiar with graphical calculus, and if not, doesn't matter, but it's important that we have these maps. The other thing that we will ask is that this unit element is a simple object in my category. This, I mean, simple as an abelian category. It's a simple object in my abelian category, so it doesn't have other sub-objects than itself and the zero object, the zero object here. And then finite is a condition only again in the abelian structure, and it's asking me a lot of things. Let me tell you more or less what they are. I will ask, first of all, or one of the things that I will ask is to have enough projective objects. So in these abelian categories, we can define projective objects, very similar to what you do in when you have modules. And we will want every every object to have a projective cover, which is again defined in the same way as for modules. In this abelian context, we can also have a Jordan-Helder series. And so we want all our objects to have finite length in this series. So these are all finiteness conditions, as you are seeing. Then we want finite rank. And what is finite rank? Finite rank means that I have only finitely many simples up to isomorphisms. So in my categories, I can have a lot of indecomposable objects, but simples, I will have only finitely many up to isomorphism. That's very important in this finite condition. And the last thing is that these home spaces in my category are vector spaces now. I will even ask that they are finite dimensional vector spaces. So, and the main examples to keep in mind are not the only examples, but the main examples to keep in mind are rep G for a group or rep H for a Hopf algebra. At least for this talk, that's what we will be thinking, but they could be more general. They don't need to have an underlying vector space that you think of for the object, for example. And there are some nice, interesting examples by Ettinghoff and Benson and, Benson and Ettinghoff, and Benson, Ettinghoff, and Ostricht in characteristic P of very nice finite tensor categories not coming from Hopf algebras, for example. So what are the motivating questions that we thought with Sarah first, and then we extended with Peter some of these things. So the motivating questions were first in finite dimensional Hopf algebras. So if you give me a finite dimensional Hopf algebra and two finite dimensional modules, what I need to require in H, or what is sufficient to require in necessary or sufficient to require to H, in order that if I have that the tensor product of M and N is projective, that happens if and only if the tensor product of N and M is projective. So here you see that I'm basically interchanging the order. They are not necessarily isomorphic in general. And the question is if we could determine the projectivity of one in terms of the projectivity of the other. And then another question is, in a finite tensor category, some things that come from the rigidity from this existence of dual are two things or more things. But one thing is that the tensor product is exact in both variables. So if you tensor like this is exact, so takes exact sequence in exact sequences, and the same in this direction. This follows from having duals. And the other thing that follows from having duals is that if I have P projective and X is an object, any object, then tensoring my object X by the projective give me a projective. And doesn't matter in which order I tensor them. This is because of rigidity, because existence of duals in both left and right duals. So now one question is, what I need for insurance that M tensor, M to the nth power, here is tensor powers, is non-projective if I started with something that it's non-projective. And the last question that I haven't defined this yet, but one of the things that we will care about is what I need for my support variety to respect or to have the tensor product property. That is, if I look at the variety of the tensor product object, what I need for this to be the intersection of the varieties of the objects that I started with. So these are kind of the motivating questions. So let me tell you, I need to tell you a little bit about the cohomology of finite tensor categories, because we will use cohomology to define the support variety. I don't know if you have questions up to here. Okay, so to define the cohomology of the finite tensor categories, and this is it's the same as we do for cohomology of Hopf algebras. So we start by first looking at xn of xy. Here xy will be objects in C. Maybe let me say that xy are in C. So I'm looking at this x with respect to my category C. And what is this xn? It's just equivalence classes of n extensions of x by y. So what I mean here, I just mean an exact sequence of the following shape. And this must be an exact sequence in my category C, meaning that here I need to have arrows in C, and I want this to be, yeah, an exact sequence in C. So that will be my X. And now I want to define the cohomology of C. And how I will define it? I will define it as the self-extensions of one. So I will start with one here and end with one here. That's what I'm asking for, all the extensions of one by one, basically. And so I take that, all the possible extensions. So I will be changing n for all n bigger or equal than 0. And then I will do the direct sum. And that will be the cohomology of 1 to 1. And that's the cohomology of C for us. That's the definition. Maybe here I should put extension, sorry. But yeah, are all the self-extensions of 1 to 1. Now, this is a nice gadget. It's a graded commutative algebra. These are results of Mariano Suarez Alvarez, for example. And then what we will do is we will define h of x. So basically this is h of 1 here. And now we will copy this idea and we will define h of x. And how we define this is, again, maybe let me write it specifically, but I look at all the self-extensions of x. So I look at the extensions of x by x of different length. And I look at the direct sum of all them, and that's this hx. And what is nice is that this is a module over the cohomology of the category. How we give the module structure? Imagine that you have, maybe let me make here a comment. Let's say that you have this extension here from 1 to 1. And now instead of having, sorry, I started kind of incorrectly. No, yeah, I mean, it's fine. It's the same idea. But yeah, imagine that you want, maybe let me say, so the action will be induced in the following way. This is what I wanted to write. We have a map that it's the map that I was going to write there, that it's phi sub x, that if I start with any extension of 1, I can get an extension of, sorry, and I forgot the one here, of x in the following way. What I could do to get the extension of x, imagine that basically what I want is to change here 1 and 1 by x and still have an exact sequence. So what I will do is I will apply this map phi x, which is exactly or kind of induced by tensoring by x. Remember that I told you that tensor is, or is by the tensor product is be exact, so it's an exact, this is exact, so takes exact sequence in exact sequences, and x tensor 1 is isomorphic to x, and here we have these things here. So I will get an extension in this way, and this now induces an action here. And then something important about this cohomology is that there is a conjecture that actually comes from a long time ago and inspired by some other questions, and I will talk a little bit about the history in a minute. But there is a conjecture that I told you that this is a graded commutative algebra, and this is a module over this algebra. So there is a conjecture by Tinkoff and Ostrich that for any finite tensor category C, this is actually a finite generated algebra, and for every x, this is a finite generated module over the cohomology. So this is called the finite generation conjecture, and I will be mentioning a little bit about that. I will assume that my categories have this property in most of what I will do. So I will not go in complete detail on the history of this conjecture because it's not the main topic of the talk, but I wanted to tell you that there is a lot of efforts on this direction. As I mentioned, this started, even if Tinkoff and Ostrich conjectured it a couple of years ago, or maybe like 15 years ago or more, there was earlier work on other contexts that were already going in the idea of this conjecture. So as you see, there is work in characteristic 0 and work in characteristic P to prove this conjecture, and there is work by Friedlander and Partial for enveloping algebra or restricted enveloping algebra, and Ginsburg and Kumar about small quantum groups. This very important work of Friedlander and Susslim about finite group schemes that is related with co-commutative Hopf algebras, and then work in characteristic 0 about Hopf algebra with a abelian group of group likes with specific types, or small quantum groups work by Gordon and also Bendel, Nakano, Partial, and Pillian in 2014. There is also work of Dupresky in characteristic P, or in positive characteristic for supergroup schemes, not just group schemes. Then Friedlander and Negron, and also Negron, were studying Drinfeld doubles, or Drinfeld doubles of some Frobenius kernels. Then with Chris, we studied how this finite generation and how the cohomology changed under some standard constructions of Hopf algebras and from tensor categories, like taking the center of the category, or looking at Morita equivalencies, which is related with some deformations by cocycles in the Hopf algebra level. And then also last year, Andruszkiewicz and Hionop, Sova, and Witherspoon proved the finite generation for Nichols algebra of diagonal type. And I think I should say that also Benson and Ettinghoff proved the finite generation for this new family of symmetric tensor categories in positive characteristic, and I forgot to include it here.
Sorry, can I make a comment?
Yes, of course, please.
Yeah, so the earliest sort of result was probably the Evans-Minkoff result in the 1960s for group algebras.
Sorry, I didn't understood. I didn't hear.
Sorry, the finite generation for group algebras was in the 1960s by Evans and Minkoff.
Yeah, and actually that should be kind of the first thing. Yeah, that was the first big step. Yes, you're totally right, and thank you. So now let me tell you about the support varieties for finite tensor categories, and I will make some disclaimers after this, after the definition. So again, I will be working with a field of algebraically closed, finite tensor category, and I will ask this category to have the finite generation property. So be a finite generated algebra, the cohomology, and all the modules will be finitely generated modules over the cohomology. And again, I will use this map that we just saw about going from the cohomology or from the self-extensions of one to self-extensions of X via tensoring by X. This is what gives me the module structure. And what we can do is we can look at when we look at this H module structure, one question is we could look at the annihilator of this action. And this will be a two-sided ideal. And this will be a very important ideal that we will use. We will define the support varieties in the following way. So the support of the unit or the support of variety of C will be the maximal ideals of this homology. And the support variety of X will be the maximal ideals in this quotient that I can do, here using the annihilator that I just mentioned. So are all the elements, I will do the quotient and then I will take, sorry, this doesn't look, I'm missing a parenthesis here, to this quotient here, and I will get the maximals ideal here. So some disclaimers that I want to mention is, first of all, finite generation is not needed for the definition or basic properties. But to get nice homological info, we need it. So I will tell you a little bit about when we use it. We use maximal ideas approach, but you could use prime ideals, and some things need to be checked, but depending on different things that you want to look, maybe prime ideals are better. And I know that, Dan, you work with prime ideals for looking in Balmer's geometry and spectrum and all this. So I know that there are these two sides of the stories, and we think that both work pretty similarly, and we are looking into this. And actually, this support variety could be defined in different contexts. For example, for triangulated tensor categories, that there is work from One Cross, Schnaschel, and Solberg, and actually with, maybe I will mention in progress, with Peter, Bergh, and Sarah. So my co-authors, we are working on talking about module categories over finite tensor categories, which is kind of a representation theory of finite tensor categories. So there are other contexts where these kind of questions are also studied. So let me tell you what nice properties we prove for support variety. So with Peter and Sarah, we prove the following. And for this first nice property, we do need the finite generation condition to be true for our tensor category. One very nice thing of the support varieties is that they can recognize projectivity of the object. So the object is projective if and only if the variety is trivial. Then other thing is we have the abelian structure. For this, for example, for these two, I don't need the finite generation condition, even if I'm assuming it. So we have the abelian structure. We can do X direct sum Y, and we want to know how the variety, the support variety, behaves with respect to this, and actually behaves nicely. It's just the union of the varieties. And the other natural thing to ask is, in these abelian categories, we have the short exact sequences, how the varieties behaves when you have a short exact sequence. So if I pick any, I need to pick my three elements, but in any order, what will happen is that the variety of one of them is inside the union of the varieties of the other two. And I could choose, but I do need to have this equality here, but I can choose in the way that I want the 1, 2, 3. That's what I'm doing. One other thing that we proved, and this is a generalization of a very beautiful result from Carson for finite groups, is that if we have a indecomposable object, then the variety of this object is also very nice, is a connected variety. And here we need to do some different tricks because some things don't work as nicely for this kind of general tensor categories that in the group case work better in the category of representations of group. For example, the variety of an object, it doesn't need to be equal or isomorphic to the variety of the dual. And that was kind of used in some of the arguments, and we need to do a detour, but still this nice result from Carson can be generalized to this context.
Sorry, is it the variety or the projectivization?
Sorry, can you repeat? I couldn't hear.
You need to projectivize the variety for it to be connected. I mean, I don't think it's.
You mean projective variety? I didn't understand that part of the.
This is a homogeneous variety, a high homogeneous variety. So you can projectivize. And I think the statement is that the projectivization is. We can check on this.
It's probably automatic that the non-projectization is connected because everything can be connected to the origin.
Yeah, to be honest, when I defined some of the things here, I wasn't very precise. Maybe if you're in characteristic 2, you need to do a little bit of different things here. I don't know if that's where you are asking. That's where your question is coming from. Maybe.
No, what I mean is if it's a cone, it's connected anyway because anything can be connected to the origin. So the statement would only really have content.
Well,
if you talk about the projectivity.
Well, so you have to projectivize it.
Yeah, because I mean any cone is connected to the origin, So,
yeah, so you have to project.
Okay.
Okay.
Yeah, and the other thing is about the tensor product, and it's coming back to one of our questions, and it's what can we say when we have the tensor product, what we can say about the variety of the tensor product. And actually, in this case, we can just give an inclusion, and it's included in the variety of the first object. If my category is braided, which I haven't defined for you, but just keep in mind that if the category is braided, the tensor product is commutative in a nice, very coherent way. So X tensor Y is isomorphic to Y tensor X. In that case, our variety will be included in the intersection of the varieties. And I promise that I'm almost done. Sorry that I'm running out of time. So some questions follow up from here are when we have the equality and not just an inclusion. And it's known for some cases. So I didn't explain all this, but I will mention some cases. With Peter and Sarah, we proved that it's true for some kind of objects. These are, again, a generalization of very nice objects introduced by Carson in the group case, and also studied in the triangulated case called COSUL objects. In that case, we define it in the tensor categories, and we call it Carson objects, and it's defined in a very similar way than for groups. It's very nice because if you have X to be the Carson object and Y to be any other object, then this is true always. So like these Carson objects are good for the tensor product property. Then it was proved by Friedlander and Pevsova that for a co-commutative Hopf algebra, so finite group schemes, this is also true for any objects in the category. For quantum groups, or actually for some quantum groups, there is work of Negrona and Pevsova and from Dan, Vajau, and Yakimov, both from last year. But this is not always true. And actually there are counterexamples. And if C is not braided, it's when these counterexamples happen. And braided, remember that it's this possibility of having commutativity of the tensor product. And first, there are some nice examples of Sarah and Benson in characteristic or in positive characteristic. And then with Sarah, when I was a postdoc at Texas A&M, we give more examples in characteristic P, but also we generalized to or not generalized, also give examples in characteristic 0, but actually was a kind of similar construction to this one, but changing some of the things. So maybe in 1 minute, let me tell you, I will not tell you much more about the example. So we start with finite dimensional algebra, and we have also a finite group acting in our algebra. in that way, we can create something called the smash product that was introduced by Molnar. That is kind of a semi-direct product of these Hopf algebras. So this as an algebra is just the tensor product of algebras, but the coproduct or the coalgebra structure is a kind of a semi-direct thing. You use this action to twist it a little bit. And then if A and G are here and A satisfies the finite generation condition, also K does it. And then what we did was construct an example. In that way, we started with a Hopf algebra that has the finite generation property and also the tensor product property. And what we did was consider the smash coproduct using 2 copies of this algebra and the algebra function of set 2. What was the action? Just swap the factors. And then this K does not have the tensor product property. And moreover, these tensor product of M and M are projective, even if M is non-projective. And M tensor N is projective, even if both M and N are not projective, but this one could be still, this one will still be not projective as they are. So thank you for listening and sorry for going over time.
So I just have a comment.
Yeah.
So in the work that I have with Kant and Milan,
Yes.
so this is the second paper.
Okay. The second paper. Mm-hmm.
Yeah, so we actually look at the tensor product, this question up here, this tensor product property, and it's very much related to the prime ideals in the tensor triangular geometry.
Yes.
So, so you can define prime ideals like you would for non-commutative ring. And then you can define completely prime ideals. So whenever you have completely prime ideals being defined, it turns out that you can actually deduce this. So there's a condition which automatically gives you the tensor product using this sort of hybrid structure.
Yeah, that's very, very interesting. Yeah, I have seen some talks by Kent, I think, that are very interesting about that work. Yeah, and I think that's one of the interesting things about the tensor property, because since we saw it's not always true and we can construct kind of easily some examples where it's not true, even if we start with something true, but it's interesting that it's related to this idea of thick ideals or prime ideals and so on. Mm-hmm.
And then, so one thing that Chris and Julia observed was like in a small quantum group of the realm, then right ideals are actual ideals. So it turns out that that actually gives you this equivalence between completely prime and prime ideals. So that connects up very nicely with this sort of general. Mm-hmm. So, but there are a lot of other questions sort of involved. We don't really know if the conditions are both necessary and sufficient.
Mm-hmm. Yeah, that's interesting. And yeah, there are a lot of good questions around these things. Yes.
Good questions. Okay, if not, let's thank you again.
Thank you all for having me here and for listening.